All right. Good morning, everyone. My name is Krishnakumar. I go by KK. I'm a product marketing manager with the FPGA business unit at Microchip Technology. Today, I'm going to be talking about the LED cube. We built a little LED cube using one of our SoC FPGAs called PolarFire SoC that's based on RISC-V architecture. So in this session, I kind of like the demo theater sessions where we get to talk about demos. We get to talk about real problems that engineers face in using different products, how we combine different technologies together, different hardware and software together, and come up with innovative solutions, right? So one of the things that we started working on is this, an LED cube. So I'm going to go over what it took us to get to this product right here. To begin with, credit to the creator. So we didn't do everything, right? This, what you see on screen here is actually an open source design that's available from Adafruit. Okay, it is an open source project that's published out there, and it's based on Raspberry Pi. Okay, we looked at it and we saw that there's like thousands of LEDs on it, and it's been running from a Raspberry Pi. We were just curious, how do you go about doing that, right? So one of our engineers named Darren Wen, he's actually a technical fellow at Microchip. He was just curious and he wanted to see what it took to build such a system. All right. So he actually leads our field-based software engineers, and he has a doctorate from University of Reading. Okay. He was curious and he wanted to figure out a way to implement something like this using our PolarFire SoC FPGA. So how do you do such a product like this? What does it take to actually build an LED cube like this, right? You want to play videos on LED panels. You may have to do some sort of graphics processing there. You're really talking about controlling a bunch of LEDs. What you see here is actually 6 panels of 64 by 64 pixels. That is actually 24,000 LEDs. To be honest, these are RGB LEDs, so in fact, it's close to 75,000 LEDs are being controlled in this system. It's not really an easy task for a microprocessor to do it. What does it take to implement this in Raspberry Pi? In fact, we found that the original design that was run from Raspberry Pi, it uses its internal GPU, and the processors in the Raspberry Pi were actually used up to 60% to run this thing, all right? But we wanted to take a look at what we can do with one of our products, okay? Introducing BeagleV Fire. So this actually is a product of an open source nonprofit ecosystem called beagleboard.org. Okay? We partnered with them and they developed this board based on our SoC FPGA, the PolarFire SoC. So the PolarFire SoC is actually a 5-core RISC-V processor, 64-bit RISC-V processors that runs up to 600 megahertz, okay? Not the fastest out there. But then this SoC FPGA also has an FPGA fabric attached to it. So the chip that's used on this board actually has 23,000 logic elements FPGA fabric, and it has transceivers that go up to 12.7 gig, okay? And BeagleBoard used this chip to build this board called BeagleV Fire. Now, what's great about BeagleBoard is that they build a whole ecosystem around boards like this. The 2 connectors that you see on the top and bottom, that's kind of their standard connectivity. Like you have shields in Arduino, hats in Raspberry Pi. The daughter cards that plug onto BeagleBoards are actually called capes. And that's a standard form factor, standard connector out there, and you can build your own custom modules and then plug onto this board and create your own extensions. And there are, of course, hundreds and thousands of people who actually develop these and then just publish them open source. And you can get them, many of them you can even buy and then use with BeagleBoard. Okay, so we wanted to actually develop this cube using this BeagleBoard, right? So let me go through a little bit of detail about what's in the BeagleBoard, okay? So to talk about the PolarFire SoC FPGA. I'm not going to do a product presentation. It's a quick look at what's inside. See, all the orange blocks that you see here, that's what you're interested if you are an embedded developer. If you're a software, firmware developer, all the orange bits forms the microprocessor subsystem. It has the 5 RISC-V processor cores, the caches, the DDR controllers, and a host of peripheral IPs that you can communicate with. All right? If you're an FPGA developer, the blue bits are the ones you may be interested in. That's the FPGA fabric, the 1.6 gig fast I/O and 12.7 gig transceivers, PCIe interface, and so on. All right? There is an AMBA bus or AXI bus that connects these two within the chip. So you get to develop your own custom hardware on the FPGA fabric, and then you can control and communicate from the microprocessor subsystem. The microprocessor subsystem actually runs Ubuntu in the Beagle board, all right? So these two together form the bulk of what PolarFire SoC FPGA is. And we wanted to look at developing a system like this where there is some amount of serial processing. You may want to run like a video player and then control a whole lot of LEDs. We thought that an SoC FPGA was kind of ideal to port something like this. Now, if you're a software developer, if you're an embedded systems developer, you might think that FPGA is kind of out of your expertise and you may not have the capability to work on FPGA tools. But BeagleBoard actually has simplified that for you. With this, they have a solution called the BeagleV Fire Gateware Build System. So essentially what they've done is create a repository of different bit streams that you can program on the FPGA fabric. And these bit streams or these binaries come with a gateware device tree overlay. All right. So you have these bit streams that you can program on the FPGA fabric, and there's a device tree overlay that actually tells the Linux world or the microprocessor world what's programmed in the fabric. So at any point of time, you can program, let's say, a MIPI camera interface with an image pipeline on the fabric and then use that as a camera. Or you can have a high-speed serial interface connected to an A to D converter and have a complex analog system built into it as well. And this whole build system kind of helps you to program different things in the fabric and use it as a different processor each time. All right. So even for embedded firmware developers, without knowing how to work with FPGAs, you can very easily use this system and program different things on the FPGA fabric and kind of operate it as different microprocessors every time. All right. So that's essentially the fun part about working with BeagleBoard. It's easily usable, easily accessible, even for just embedded firmware developers. Okay. So now, what I'm going to do is go through what it took us to actually build this system. So to begin with the hardware design, which actual the LED panels and the hardware, and then I'll talk about how the software was designed and how they all came together. Okay, so to begin with, we just started using what was already used by the Adafruit project. So the same LED panels that are available from Adafruit, we just used them. Actually, these LED panels use something called Hub 75 interface. Each panel is a 64 by 64 LEDs, and 2.5 mm pitch, and so on. So a closer look at the panel, you'll find, let me see if I can use a pointer. All right, so you find two connectors, one on the left here and one on the right. They are the same connectors, but then one is a data in, the other is a data out. And it's a 16-pin interface, and what it does is it lets you connect multiple panels in a daisy chain. You can just connect one next to the other, one data goes in and out of the other two and back into the next panel. So you can build a huge chain of LED panels together and then control them from a single processor. What we also did was build a little cape. It's a little board that we designed for the BeagleBoard that plugs on top of the BeagleBoard, and then it provides the interface to the LED panels. Okay, so we also made this open source. So the BeagleV Fire and the relevant documentation is available. The Hub 75 panel, this kit board is available, and then you just plug them together. You now have a system that can control these LED panels. So I've been talking about Hub 75, but not with a lot of detail. So just a quick info on how this thing works, because we're talking about controlling 75,000 LEDs. How do we do it, right? So Hub 75 is a standard interface that's commonly used whenever you're using LED panels and matrix LED displays. It consists of a 16-pin interface that you can see here. There are 5 address lines, and essentially that means that you can address up to 32 rows of LEDs. So, and then there are 2 sets of RGB pins. So essentially, a 64-row LED panel is split into 2. The top 32 rows and the bottom 32 rows, and 2 sets of rows are written every time. And then you have your clock latch and output and enable control pins that control how you turn on and off the LEDs. Okay, so the entire display is actually kind of implemented like a shift register. So what you see on top, these are the red line, the green line, and blue line, and these are all individual shift registers that control the data. So you send your RGB information in parallel, and then you send in your clocks, and your data gets shifted across the LED panel. And each panel here is a 64-bit wide. So 64 LEDs form this shift register. All right. So in an actual panel, there are obviously 2 sets of them. So one on top and one on the bottom. So 2 sets of shift registers implements the top half and the bottom half of them. And for us to implement a cube with like 6 sides, we're going to actually daisy chain 6 of these boards together. What that does now is that you have shift register that's like 384-bit long, and essentially the number of panels into the panel width. All right? And let's take a quick look at the display sequence. All right, so to start with, you set the row address. So row 0 is selected. The top row and the row 32 get selected. And with the 2 sets of RGB inputs, you just clock in. You just clock in the values of each of the LEDs that you want. All right, and then you latch them, and then you enable the output that would turn on the individual LEDs that you want to turn on. And then you move on to the next row and then repeat the whole thing. So that's how the top half and the bottom half of the LED panel gets refreshed every time. Okay, so this is basics of how LED panel drive happens. But what's interesting is that we did not use a microprocessor to do all this. If you were to use a microprocessor to do this, there's a lot of PWM that you need to drive. It's quite complicated. But when you do it on an FPGA, this is a pretty simple implementation. Now, what I've told so far is about just turning on an LED on and off, right? But then there is also an effect of shading. How do you go about doing shading, like having different shades of bright and dark, right? So there are several ways of actually tricking the brain to think that an image has depth. You may be familiar with what's called pulse width modulation. A PWM, you kind of tend to vary the duty cycle of your pulses to vary the brightness or darkness of a single pixel, right? What we did here is what's called as binary coded modulation. Essentially the same thing, but then it's more user-friendly because you're operating with binary numbers. What this does essentially is that adds weight to individual bits and then turns on and off the outputs to these LEDs based on the bit position. So for instance, if the brightness level you want for a particular cell is the number 25, that's written here. So the first clock pulse for 1 clock cycle, it's on. And then there are 2 zeros here for bit 1 and bit 2. So 2 clock cycles and 4 clock cycles, it's off. And then 2 ones here. So 8 clock cycles on and 16 clock cycles on. So essentially, So it's on for 25 clock cycles out of 31 and about 80% duty cycle. So it kind of simplifies how you can implement shading or pulse width modulation in using an FPGA. All right. Now coming to the system architecture, what I've told so far is like the complicated parts for a microprocessor, we've significantly simplified by implementing them on the FPGA fabric. And I want to show you how it all now comes together with the system architecture, right? On the Beagle board, the central brain of the system, the RISC-V microprocessor, is right here. On one end, you have the set of hardware interfaces that are available with the system, the LPDDR4 memory, eMMCs, gigabit Ethernet, and all that. And then in the bottom, you have the FPGA fabric, where you can implement several different logic within them. So you have hardware implemented within the fabric as well. In this particular system, we have implemented what's shown here. So the CAPE implementation. What it essentially has is an APB bus. So this is the bus AMBA interface that's implemented between the microprocessor system and the FPGA, so that you can communicate and control the IP blocks that are implemented on the fabric. We've implemented some frame grabbers and control registers, and then we've done some conversions. So Linux, the Linux world likes to use 32-bit color in their video playing, right? But in a pixelated system like this, where each pixel is the size of a Lego, it's going to look pixelated anyways. So we did a little conversion to make things simpler for the design. So the 32-bit is now converted into RGB 565, and that's done on the fabric. And then we take care of the other timing generation, IO mapping, etc., to take care of controlling the LED panels. Okay, and then that's it. So this is all that happens on the FPGA fabric. Now, what happens on the microprocessor? So we are here for the RISC-V Summit. So what are we doing on the RISC-V processor? All we are doing is running Linux. The Linux has a frame buffer drivers enabled in the kernel. And we've installed a video player on the Linux. And all it's doing is playing a video. And the video is routed to the FPGA fabric through the APB interface and the frame buffer that's implemented on the fabric. And it's just transported out to these LED panels. All right, simple as it gets. If you want to try this yourself, you can. It is quite easy to do it. We've actually published all this online, and it's open source, available for you to download and use. We also have the schematics, layouts, as well as the designs, and there is a good amount of documentation that you can use. And recreate this, explore more things that you can do with it. Okay. So finally, to summarize, the whole activity is just a fun project we did to pick something that was implemented on a Raspberry Pi, and it was kind of heavy load on the Raspberry Pi in the first place to run all this. So and what we did is try to port that on an SoC FPGA and see how does it work. So once we implemented, we looked at, can the CPU do more? We have a quad-core RISC-V CPU that's running at 600 megahertz, compared to a Raspberry Pi that's quite low. So what else can we do? Is the CPU, can it do more? Sure. So the CPU usage is almost nothing. All it's doing is running Linux, and it's playing a video player. Okay. So there's one core using about 28% of resources. The other three cores are just not doing anything. They're just getting bored. What about the fabric? Can we do more with the fabric, or have we completely used up the fabric? We've used about 23% of the FPGA fabric. So this is the smallest FPGA fabric you can get in this family, the 23K logic element family. And this whole implementation barely uses a quarter of the FPGA fabric. There are FPGAs in the same family available that is 20 times larger. So a significantly more capable SoC FPGAs are available within the same FPGA family. All right. So in effect, we took a system that was running on a microprocessor, and then we ported it on an SoC FPGA. We kind of partitioned the system architecture into certain things to be done by the fabric, certain things to be the microprocessor, and essentially using them the most efficient way possible. All right. So with that, I would like to close by saying that I encourage everyone to explore the world of SoC FPGAs with our BeagleV Fire. All right. Thank you very much. Thank you. If you're interested to find out more, we have this board, this demo available at the Microchip booth. Please come and talk to us. We'll be available today and tomorrow. Please feel free to reach out to us. Thanks.